Just do a brief review of that. Okay, so if we let me share this. So you might remember we were looking at statics, basically static systems, and we looked at what are the governing equations, and we looked at the problem of earth pressure, which is the simplest problem that we can solve in statics. And then we started on this problem of stress in a rectangular bin. So, if we look at two-dimensional systems, then these are the stress equations. This is the stress balance in the x direction. This is the stress balance in the y direction. So what we said is, look, there are only two equations and we have 1, 2, and 3 unknowns. So we need one more equation, and that equation is given by this condition of incipient failure, which is what we say is that at any point, the system is always at the yield point. So sigma m by tau max is equal to sine beta. That is the condition for yielding. And this is exactly equivalent to saying that the maximum to minimum principal normal stresses are in the ratio k, which is 1 plus sine beta divided by 1 minus sine beta, where beta is the angle of internal friction. So this way we have a complete set of equations. There are 3 equations and 3 unknowns, and we can solve problems. And then the simplest problem that we could solve was this, where you have a infinite system in the y and z direction. And when we simplify the equations, we see that the pressure or the normal stress increases linearly in the x direction like this. The shear stress is 0. And then for the stress in the y direction, normal stress in the y direction, there are two possibilities. One is if you have an active state, that means this stress is more than the other stress. So the system is active and the surroundings are passive. That is why sigma yy is less than sigma xx, and so Ka is less than 1. So this is actually sigma max and this is sigma min. And you can have a passive Rankine state in which the system is passive and the outside, where the surroundings are applying force onto the system. In that case, sigma yy is greater than sigma xx, and your Kp is greater than 1. So in this case, this is sigma max, this is sigma min. So this we have already seen. And then we went on to the next one. And this, what we showed, of course, is that in this case, all these terms are non-zero. And since the gravity is only in the x direction, so here we have rho b into g. Rho b is the bulk density. I've been saying this word many times. What this means is actually it's the particle density multiplied by the solid volume fraction. Okay. So it's actually the total mass of solids divided by the total volume. That's why we write it there. Okay. Now, we did a lot of algebra and we showed that if the system is in a condition of incipient failure, then you can actually write an expression for sigma yy in terms of sigma xx and xy like this. I'm sorry. And once this is done, then you again have 3 equations and 3 unknowns. And here you have many more boundary conditions. First, at the free surface, all the stresses are 0. So that at x equal to 0, this is 0. At y equal to 0, that at the midplane you have symmetry, so that both of these are 0 due to symmetry, and also sigma xy is due to 0 due to symmetry. And at the side wall, you have the shear stress is mu w times the normal stress, and mu w is the coefficient of wall friction. So this is our system that we are looking at, and for a smooth wall solution, that is when the wall is frictionless, then mu w is 0, so you get sigma xy equal to 0, and essentially that all these equations, these equations just become the same as the Rankine solution, because if sigma xy is 0, both these terms are 0. So you just get sigma xx is linearly varying with, so sigma xx is just rho gx, and sigma yy by d sigma yy by dy is 0. That means sigma yy doesn't vary with in the y direction, which is in this direction, only varies in the x direction. And then you can get this. And then we can simplify this equation by putting sigma xy equal to 0. So then you have this by integrating the x normal stress, x stress balance, and then the incipient failure condition just becomes this, because the sigma xy term goes to 0. So if we take the square root of this is nothing but sigma xx into sine beta. So it can be combined with this. So you'll get 1 minus 2 sine beta plus sine beta squared. So that is 1 minus sine beta whole squared. And so if you simplify it, you'll finally get this. So this is exactly what we got for the Rankine solution. Okay. And now what I want to do is, in today's class, I want to just give you another sort of solution to the Rankine problem, and then I'll talk about how to solve this problem for 2D, an approximate solution to these equations that we have put down. So these equations are quite complicated. In general, you have to do it numerically, but how can you do it some approximate way? That was done in 1895 by Janssen. So I'll show you what that solution is. And then we'll discuss a little bit about how to, instead of statics, if we want to do slow flow, then what are the possibilities? Okay. So let me show you this. We have learned lamps. So now we can try out and see if, uh, using lamps we can get anything close to the Rankine solution. So this is the presentation that I have, short presentation on using lamps for computing the Rankine earth pressure. So I decided to look at a very simple system which is 2D. So you can imagine just one layer of particles in the XZ plane, and in the Y plane the thickness of the system is just one particle diameter. We consider particles of diameter 1 centimeter, density 2.5 grams per centimeter cubed. The W we'll take to be 50 centimeters and about 3,200 particles. And then what we do is we pour the particles from the top, allow them to settle under gravity, and then compute all the components of the stress. Now, because we are taking just a few particles, there are many fluctuations. So I have to keep doing this many times and then calculate the average over all those configurations. So what results I'm showing you is for 500 configurations. And this is the script. So you can see that this is the standard thing we always use. Then the boundary in the X direction, we have a periodic boundary condition. That means in this direction, as I mentioned, periodic boundary condition. That means particles going out from here will come in here, and also any stress applied by a particle here will be felt by the particle on this side. So that's why I have periodic in the X direction but fixed in the Y and Z. Of course, Y direction doesn't matter. And I take a block which is 50 particle diameters wide and 100 particle diameters high, and 1 particle diameter in the Y direction. Make the box, then read the data, read the base data. So this will just be particles on a grid. Apply the reflecting boundary condition in the Y and Z direction, so particles don't escape in those directions. This is to specify that we move the particles, only the mobile particles, because there's a rough base that is added and there's a gravity of 981 centimeters per second squared in the minus Z direction. Then we compute the stress. This is to write all the data X, Y, Z, Vx, Vy, Vz, and the stress components. This is sigma xx, this is sigma zz, and this is sigma xz. So the two normal stresses and the shear stress. And then of course we run it for 200,000 steps. So it has to settle and then completely become static. So this is what one configuration looks like. And you can see that there is a lot of, sort of non-uniformity, you can say. So darker the color, higher the value of stress. And you can see what is actually happening is that, when you have very dark lines, you're actually seeing chains of stress where, there's a chain of particles and the stress is propagating through those. So in the X direction, the stress is going like this. In the Z direction, you'd have this. And in the XZ direction, they are at 45 degrees. But you can see there are these dark chains, and these chains will essentially, they are the ones where the stress is being propagated. In fact, in XZ, there will be some negative and some positive. So the negative ones are the very light, and the black ones are the very positive, very negative, and the red is 0. That's why the free surface you're seeing this red color. So this is what you get in one configuration, but you have to do it many, many times. And then what we do is we bin all the particles, make horizontal bins, divide it all into equal size bins, and we calculate the stress in each bin. Hence, we can get, for example, we can get sigma xz as a function of z, where z is this distance. And so we can do it for many configurations. I did it for 500, and this is the sort of result that you get. So this is z, which is the distance. This is the base, and on this side I've plotted the stress. This is in dynes per centimeter squared. So everything is in CGS units. And what is interesting is that here you can see there are, just to remember, this is the z direction and this is the x direction. So, if you look at sigma zz, that is in the direction of gravity. That is the red line. And you can see that you get nice linear variation. This is exactly the Rankine solution. This is what you would have got, linear. And then what you see is sigma xx, which is the one in the transverse direction, that is also varying linearly. And if you see this, the ratio of these two, it's a constant because both are linear, so you can take the ratio and you see that you get a value of k to be 1.3, and so the angle of internal friction is 7.5 degrees. It's very low friction. So this is one validation of the simulation of the theory that we just did, and you can also try out this. I'm going to put the program and everything on the website along with this presentation, so you can try out and make some changes if you like. Okay. So any questions? So if there are no questions, then I'll go on to the next part. So I want to continue from here, and we are looking at stress distribution in a rectangular bin. We have got equations 1, 2, and 3. Now, one of the things you can definitely say is that this cannot be solved. I mean, it's not easy to solve this analytically. So we can do another. We did one simplified case already, which is frictionless or smooth walls. And for that, we essentially get the Rankine solution itself. So now let us look at the next what should I say? The next level of complexity, and that is when we have another approximate solution. So instead of using smooth walls, but we can say that we will do an average over the cross section. And you'll see that even to do this, we need to make some approximation. It's not an exact solution. So what we'll do is, let us look at equation number 1. This equation, which is the X stress balance. So we have this del sigma xx by del x plus del sigma xy by del y is equal to rho b into g. Now what we'll do is we'll integrate with respect to y. Remember, in this one, a coordinate system is defined in this way, that y is in this direction and x is pointing downward in the direction of gravity. So this is our gravity. So this, if we have to integrate with respect to y, so we are actually integrating in the cross section of the bin. So what we are going to do is integral of every we'll integrate every term with respect to y. Because this is just a constant, I can just take it out. So now if you see this, in the first term, what I'll do is I'll take the integral inside. So I'll have d by dx, and then I have the integral from 0 to w of sigma xx dy. So I've interchanged, instead of taking the derivative first, I'm taking the integral first and then the derivative of the integral. This is all right because neither of the limits are functions of x, so this can always be done. Now the second one is an integral of a derivative, so we can just straight off write down the values, and that is sigma xy evaluated at w minus sigma xy evaluated at 0. So this is the other thing. So you can see there is a simplification. And this one also, since I've integrated this with respect to w, this is just from 0 to w. Integral of dy is just w. So this is what we did. Now let's look at the boundary conditions. Again, let's look at the boundary condition on sigma xy. So we go slowly upward. Where are the boundary conditions? Here they are. And what does it say? It says sigma xy is 0 at, of course, sorry, at y, we are looking at for the y condition. Sigma xy is 0 at y equal to 0. That is one condition. And sigma xy is mu w times sigma yy at y equal to w. So this is basically what it says is this is 0 and this is mu w into sigma yy at w. And so now what I will do is I'm going to do two things. First thing is I'm going to define this. I'm going to define the average value of sigma xx to be just 1 by w integral from 0 to w. Okay, so this is the cross-sectionally averaged value of the normal stress sigma xx. So it's the integral from 0 to w divided by w, and this will have units of stress. Okay, so this is the first thing, and then I'll substitute also for the others. Now when you see this, if I have to substitute for the integral in the equation above, then what I'll get is just w into d by dx of sigma xx plus mu w I'm applying the boundary condition into sigma yy, which is evaluated at W. The third term is just 0 is equal to rho bg into W. Now, so far no approximations. This is exact up to this point. So we have not made any approximation so far. Just simply did an integration. Now we will make the approximation, and the approximation is that suppose we take sigma yy at W to be approximately equal to k into the average value of sigma xx. What is the exact, if we wanted to be really exact, I would have put sigma yy at W is equal to k times sigma xx at W. This is what I should have written. This is the exact equation. But this one is an approximation. So this is the main approximation that we make. And what that approximation says is that the value of sigma xx at the wall is approximately equal to the average value in the cross section. And this may be okay if sigma xx does not vary too much in the cross-sectional direction. So this is the approximation that we make, and when we do that, you can see that you get a nice simple equation to solve, that is and the boundary condition, of course, because sigma xx is 0 on the free surface, so we have also the average value of sigma xx is equal to 0. So this is the boundary condition. At the free surface, we must have sigma xx equal to 0. So this is what is known as the cross-sectionally average solution. And what is the approximation? Here is the only approximation that we have made. That instead of writing k times sigma xx at W, we are replacing it by the average value of sigma xx, and then we can get a nice solution. What is the solution to this? Well, you will all remember from your math classes the method using integrating factor. So what is the integrating factor for this? Well, the basic idea in this integrating factor approach is that you use, instead of sigma xx, you use some function f times sigma xx, such that when you open it out on the left hand side, you'll get two terms. So I want to come up with a factor such that I can combine these two terms into one. And I want that term to be of this form: 1 by f d by dx of f into sigma xx. Okay, so this is my, I want to combine these two terms to be, I don't know what is f, but I can find out by saying that I want f such that when I open out the left hand side, I get the right hand side. This is what I want. So what is f? So if I open out the left hand side, then you'll see that this is nothing but d of, so the first derivative, I take f out, it cancels with the f at the bottom, and I'll get this, the first term, and the second term is nothing but sigma x by f into df by dx. So this, sorry, is equal to, you can see this term will cancel with this will cancel with this. So then I get a nice thing that 1 by f df by dx is just equal to mu w into k divided by w. So this is something you can easily integrate. So you get d ln f by dx is equal to a constant. So ln f is just this constant times x. So you'll get essentially that f is just equal to exponential of mu w k x. Right? So this is my integrating factor. So if I use this as an integrating factor, then I can write my these two equations as just this one. So essentially what I have is on the left hand side now I have 1 by f. So that means 1 divided by exponential of mu w kx divided by w into d by dx of the same integrating factor into the average of sigma xx is equal to rho b into g. So now I can take the integrating factor on the other side and integrate it. So I will get exponential of mu w kx divided by w into this is just equal to, if I take it on that side and integrate, I will get mu w k divided by w into rho bg exponential of the same thing Are you catching my mistakes? Okay, so this is what the solution is. And then of course you have plus a constant of integration, which is C1. I think this is the correct answer. Yeah, rho bgw by mu k. So this is correct. Now, what is the condition that sigma xx is equal to 0 at x equal to 0? So that means C1 from the boundary condition, we get C1 is just equal to minus rho bgw divided by mu w times k. So now if I divide throughout by this, I will finally get sigma xx is equal to rho bgw Okay, so I'm sure this is an equation. I mean, we started from this equation with this boundary condition here. These are the two things we started with. And then, of course, little bit of integration. I mean, these things you can look at in any manual or any textbook. You'll be able to find solution to a first order ODE which is non-homogeneous. I used the integrating factor method, applied the boundary condition, and I got this solution. Now let's look at this. Now, first thing is, supposing I had mu w equal to 0. So what is the reduction to the smooth wall solution? That is mu w tending to 0. So if the wall becomes frictionless, then what sort of profile will I get? So you can see that if mu w is very, very small, then we can write exponential of minus mu w kx by w to be approximately equal to 1 minus mu w kx divided by w. So in this case, sigma xx simply becomes rho b g w divided by mu w into k. This 1 and 1 will cancel out, and you'll only be left with this factor, which is mu w kx divided by w. So this cancels with this, these two cancel with these two. So you just get rho b g x. So you get back the Rankine solution if mu w tends to 0. This is one check. And what is very interesting is here, of course, this one satisfies the boundary condition because at x equal to 0, sigma xx is 0 because this becomes equal to 1. Dimensionally also it makes sense. You can see that mu w is dimensionless, k is dimensionless. So here you have x by w. So this is a dimensionless quantity in here inside the exponential as required. And here also you have mu w and k are dimensionless, and this has units of stress. So this is dimensionally consistent. Now let's look at what does this thing mean in physical terms. And this is something very unusual that is seen for granular materials, but never for fluids. So here, the interesting thing that I want to say is that what happens in the limit x is much larger than w divided by mu w into k. What will happen? Can someone tell me? So basically what I'm saying is, what happens if this term inside the exponential becomes very, very large? So that is, if mu w by k is very large, what will happen to this?
So 1 equals to mu w kx by
No, say it slowly, I couldn't get it. The sound wasn't very clear.
Exponent becomes 0.
Kiran, I can't hear. I'm old.
Exponent becomes 0.
So if this term inside the exponential becomes very large, I hope this is what you all are telling me because I couldn't make out, is that this exponential will go to 0. So in that case, what you will see is that sigma xx is just equal to rho b GW. So this is the unusual behavior of the system. And if you have to plot this, if you make a plot of this graph, let's say if I plot sigma on this axis and if I plot x on this axis, so then at x equal to, oh, sorry. Let me draw it properly. So this is, let's say, the sigma axis, and this, because we are, our x-axis is pointing downward, so I'm going to draw it like that. So at the free surface, your sigma is 0, and then, when x is very small, at small distances, then you actually have this solution. So at very small values of x, you will, the same argument holds. If x is very small, then you will get this type of solution. So there is a linear behavior at short distances, and then what happens is that it will just exponentially saturate. That means that you cannot have a normal stress that is larger than this value. Let's say we call this as sigma. Oh, that is strange. So there's a limiting value of the stress. What does it mean in physical terms? That means, if you're looking at what is the stress in the system, it goes to a maximum value. If you look at the Rankine solution, what will happen is that at small distances it will be the same, but then it will go on increasing. So you have this really unusual behavior that your stress actually saturates. Even in a liquid, you will have the same sort of behavior, that there's a linear increase in the stress or the pressure as you go to greater and greater depths. Whereas for this, it just becomes constant. And this is one reason, why if you see, I don't know if any of you have ever seen petrol tanks. The stuff that is used to store oil is usually like these huge tanks which are not very high. But if you look at silos for grains, I don't know if you have seen this anywhere, but sometimes in pictures and all you might see it. Usually you will have a so it's tall and thin. Has anyone ever seen these type of containers if you're for storing grain?
Yes, sir.
Huh?
Yes, sir.
Then you have seen it?
Yes, sir.
I don't know. I usually, Let me see. I may have a picture. Some of you have seen these kinds of things, but I will try and show you a picture of it. I can't find it very easily, but I'll try. I have so many PPTs now that to keep hunting. Ah, finally I got it. So here, this is the picture I wanted to show. Usually you will see these oil storage tanks like this. See the large diameter but small height. But if you go to some farms, particularly in the West, you'll see these grain storage silos. They are tall and thin. And this is precisely the reason why, because we have now theoretically shown that um, there is a yeah, Kunal, I just saw your message that the exponential will vanish, and that's correct. So, the question always comes then, like, why, and why does this happen, and what is the reason for this? What is the physical reason for this? And we can make a very simple sort of argument that what is happening is the weight. See, the pressure is usually just the weight of the material above that surface. So if you look at any liquid, the pressure at a point is simply the weight of the fluid above that surface per unit area. That's the pressure. So where is the weight of the granular material disappearing? It cannot disappear, no? So the physical explanation is really simple. That, in our system, we have this x, y, and now if we just take a thin strip over here, let's say of thickness dx, then there is the weight of this strip is acting downward, and that is rho b g dx into w, or let's say dx into 2w actually. So that's the weight acting downward per unit width in the y direction, I mean in the z direction. And then there is this force that is acting over here. This it will be like sigma xx at x, and then there's a reverse force that is acting over here, that is sigma xx, which is at x plus dx. So that is acting in the opposite direction. And this will be there for even a fluid and everything. And if you do the balance, then you will just see that the force below is higher than the force, that is this will be higher than this by the weight of the particles. But in the case of particles, what is different is that actually you can have a frictional force, and this frictional force is mu w into k into sigma xx times dx, and that is the frictional force that really supports the weight of the particles. So beyond a certain depth, so what happens is, as sigma xx goes on increasing, the upward frictional force also goes on increasing. So as you go deeper, you see that sigma xx is increasing, and then beyond a point it doesn't increase because all the additional weight is taken up by the friction. So the basic point is that wall friction holds up or carries the weight of additional particles. Leading to a limiting stress. Okay. So this is the sort of interesting thing that one can get, and this is and I tried to show you also that there is some practical relevance to this. Okay. Now we can do many other problems like this, and I'll give some maybe in due course for you to try out. But we can now extend a little bit also and try and look at what happens if we want to look at slow flows. And I'm going to do that in the next class. That if we are looking at slow flows, then we can use a similar approach. We say more Coulomb is valid at every point because it's actually failing. And then we can also use other methods, and I'm going to discuss one other way, which is called critical state theory, in which it is more Coulomb plus it allows for changes in the density. Okay, so we'll do that in the next class. Okay. Thank you. So with that, I'll end.